Today on the Perception and Action podcast, a look at affordance-based control. Is the role of affordance perception just in action selection, or does it play a role in action control? What does it mean to know one's limits? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception and Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, I want to look at the theory of affordance-based control proposed by Brett Fagan from RPI. This topic addresses a question that I raised at the end of my series on J.J. Gibson back in episode 125. Do we really need the concept of affordances when we have information-based control? To illustrate this again, let's consider the task of catching a fly ball in baseball. A traditional ecological account of how this is done might be something like this. After the ball leaves the bat, the batter picks up perceptual information indicating that the ball affords catchability. This information could be things like the angle of the ball leaving the bat, the rate at which its height is increasing, etc. So having detected this affordance, the batter now has the goal of catching. To achieve this goal, the fielder next couples their running speed and direction to an information source that will guide them to the ball through perspective control. This could be optical acceleration or some other information source. Listen back to episode 5 for more details. So the purpose of affordance perception is really only in selecting what action we want to perform. If this is the case, is affordance perception really necessary for most of the highly specific behaviors we're talking about in sports? If we're continuously regulating our behavior based on information that is very similar to what is used to detect the affordance, do we really need a stage where the actor detects that the ball affords catchability and decides to catch it? Wouldn't it be more parsimonious to have the goal the actor is trying to achieve just emerge from the information-based control? Think about the fly ball example again. When a ball is hit, what behaviors does it afford? Catching or not catching? Is it really necessary for the fielder to perceive an affordance early in the ball flight when the information is weaker? Wouldn't it be better for them to just control their movement towards the ball based on the information, then the catching or not catching choice would just emerge? Is prospective information-based control alone sufficient to explain behaviors such as this? Let's have a look. To start off with, let's quickly review the two basic theories of the visual control of action: model-based control and information-based control. Model-based control theories propose that movements are guided on the basis of internal models of the body and the environment that mediate perception and action. Proponents of this approach adopt the traditional view that the function of perception is to create a general-purpose 3D model of the layout of the environment that exists prior to and independently of action. This internal model is built from perceptual processing of impoverished visual cues and from internalized expectations and assumptions based on past experience. Proponents of model-based control argue that internal representations are necessary primarily for two reasons. First, the perceptual cues are impoverished and require elaboration. And second, an internal model is needed to explain how our actions are guided when perceptual information is briefly taken away. For example, when you close your eyes. In general, model-based control theories assume we have an internal model of the physical space we're acting in, but other types of representations have also been proposed, including internal forward and inverse models of our body dynamics, and internal models of the dynamics of the environment, for example, gravity. The alternative view, championed by supporters of the ecological approach, is that the visual guidance of action is achieved through a tight coupling between perceptual information, specifically optic flow variables, and movement. From an information-based control perspective, the job of perception is not to create an internal model of the environment, but rather to detect information in optic flow that can be used to guide movement on a moment-by-moment basis according to some law of control. Unlike the general-purpose visual cues involved in model-based control, the optical variables in information-based control are task-specific, in that each is guided by a single optic variable, and the optic variable used in one task differs from the optic variable used in others. Each optic variable tells the actor how to move to perform a given task, but does not indicate anything about the spatial layout of the environment. Internal models are unnecessary in this view because the perceptual information alone can be effectively used to guide action. Proponents of information-based control argue that this approach gives a more parsimonious explanation of action control. One way this parsimony can be illustrated is by considering how actions are guided with respect to future events. Think again about running to catch a fly ball. It is not the current position of the ball that matters, but rather where it will be at some point in the future. Model-based control must explain how visual cues to the current position and motion of the ball are combined with knowledge of the environmental dynamics to make predictions about the position in space and time of the interception point. This is quite a complex problem. In contrast, by using prospective control, this is solved easily in information-based control models. By coupling one's movement to the appropriate optic variable, the actor will be guided to the interception point without the need for internal models or prediction. In prospective control, the perceptual information tells us about the current future. That is, whether or not our current movement will result in successful performance of the task in the future, without the need for making an explicit prediction. For the rest of today's episode, I'm going to focus on information-based control models. For more on the debate between model-based control and information-based control, please go back and check out episode 113. As Brett points out in his 2007 article in the journal Ecological Psychology, there's a major limitation with information-based control models that is often overlooked. In most models of this type, successful performance is achieved by the actor moving so as to produce the right pattern of perceptual information that, if maintained, will result in achieving the goal. Consider as an example Chapman's model of catching a fly ball, which I discussed in episode 5. This strategy involves coupling one's running speed to the speed the ball's image is moving on the eye. To catch the ball, the fielder needs to run so that the image speed does not change. That is, its acceleration is kept at 0, thus the name of the strategy. Another way to think of this is, the rate of the ball's image acceleration is telling me whether I'm running fast enough to reach the landing location in time, acceleration is 0, or whether I need to speed up, acceleration is not 0. What Brett points out is missing here is affordances or possibilities for action. Imagine that I'm running to catch a fly ball and the image is accelerating. That tells me that I need to speed up to catch it. What it does not tell me is whether or not this is still possible or afforded. What information-based control laws do not take into account is whether or not it's still possible to achieve my goal within the limits of my own action capabilities. Prospective control, whether the current future will result in success, and affordances, whether the action is possible given my capabilities, are different properties that rely on different information sources. As I discussed a few moments ago, most models relegate affordance perception to the role of action selection, while actually achieving the action relies on information-based control laws. Thus, the control problem, how actions are guided on the basis of visual information according to some law of control, is thought to follow and be independent of the affordance problem. The fact that affordances are not involved in the guidance of movement in these types of information-based control theories creates the problem of action boundaries, as Brett calls it. To illustrate this, let's again look at Chapman's model of fly ball catching. In this model, running speed is regulated so that the acceleration of the ball's image is kept at 0. The problem is that this is not a condition that it's always possible to satisfy. If there were no limits to the fielder's maximum running speed, then it would be always possible to satisfy this condition. But of course, such limits always exist, and they impose a critical constraint on successful performance to which actors must be sensitive. For example, in baseball, it's important that a fielder detects when a fly ball no longer affords catchability so that they can change their goal to playing it on a bounce or off the wall. If they don't, they could easily turn a single into a triple or an inside-the-park home run. In other words, actors must be sensitive to the location of action boundaries and behave in ways that take the limits of their action capabilities into account. If a fielder relied just on optical acceleration information to control their running, then they would never know whether the required running speed to get acceleration to 0 necessitates exceeding their maximum running speed. They would never know when they've reached an action boundary and need to change their goal. How can information-based control models of visually guided action be reformulated to solve the problem of action boundaries? Imagine all possible running speeds that can be achieved by the fielder from 0 to their top speed. This range can be thought of as a safe space in that if required running speed is kept within this region, it will always be possible to catch the ball by increasing running speed within the fielder's limits. If the required speed moves out of this range, catching is no longer afforded. So, Brett proposes that in this example, movements are not made so as to produce a particular value of optical acceleration. but instead we move so that it's always possible to reach the required running speed within the limits of our running capabilities. This is what he calls affordance-based control, because unlike information-based control, it emphasizes the importance of action boundaries, separating possible from impossible actions, and it depends on the actor's ability to distinguish between possible and impossible actions. The to-be-perceived property, like other affordances, is formed by taking the ratio of a property of the actor-environment system, the required running speed in the case of catching a fly ball, to the corresponding action-relevant property of the actor, the maximum running speed possible, leaving a dimensionless number. Okay, this all sounds good, but where do the two parts of this ratio come from? The top is easy. As we've already discussed, the required running speed is directly perceivable from perceptual information. For example, if we adopt Chapman's model, the difference between our current running speed and the speed required to get optical acceleration to 0 tells us the required amount we must increase our speed. The more difficult part is understanding the bottom of this affordance ratio, our action capabilities. Where does this come from? What does it mean to know your limits as an actor? It's often assumed that this requires some knowledge or internal model. This is an underlying assumption of model-based control, which attributes actors' sensitivity to their action capabilities to an accurate internal model of body dynamics. But as Brett points out, there is a major problem with this idea. It stems from the assumption that these internal models exist independently of perception. Quote, "These memory-based representations are not specific to the current environmental circumstance, but are instead general and thus deployable across a variety of circumstances." End quote. In the case of our flyball example, this means that the maximum running speed is represented in memory independently of the perception of required running speed. And here lies the problem. Perceived required running speed and known maximum running speed must be represented in common units for the purposes of comparison, and it's not clear what these units are or where they come from. The units of physics like feet per second or meters per second are clearly arbitrary and meaningless for biological systems. So in other words, storing in my memory the general fact that my top running speed is 30 feet per second is not very useful for controlling a specific action like running to catch a fly ball. Instead of storing this general extrinsic value for maximum running speed, Brett argues that we could use intrinsic scaling instead. Quote, "If any given unit is as arbitrary as any other unit, then perhaps the units in which such properties are perceived are not fixed, but rather flexible. That is, the visual system is capable of transforming the metric in which optical information is detected. Thus, the only units that are meaningful to perceiving acting systems are those that are defined by the ever-changing action capabilities." End quote. Evidence of this type of intrinsic scaling can be seen in Brett's work on the guidance of braking. For example, in his 2005 study, participants viewed displays simulating approaches to a stop sign and used a joystick as a brake to stop as closely as possible to the sign. Brake strength was manipulated as a between-subjects variable with 3 levels. Not surprisingly, participants who were calibrated to the weak brake initiated brake adjustments earlier than participants calibrated to a strong brake. However, when the required deceleration at onset was expressed in intrinsic units as a percentage of the maximum deceleration for each group, braking was initiated at the same mean value for all groups. So instead of storing some arbitrary value of an action capability in an internal model of body dynamics, our action capabilities are taken into account through calibration. Calibration can be thought of as a process that transforms the metric in which visual information is detected, establishing a mapping from information to movement. Once this mapping is established, actors can reliably perceive that an action is or is not within their action capabilities, and can control the action so as to stay within the limits of their capabilities. This means that there's nothing more to knowing one's action capabilities than being properly calibrated. Contrary to model-based control, actors do not need an internal model of body dynamics to behave in a way that takes their limits of their action capabilities into account. The only sense in which actors know their action capabilities is in terms of the state of calibration of the perceptual system that allows them to reliably perceive what they can and cannot do. So, as a way of summarizing, let's look at the 4 key principles of affordance-based control. Principle number 1. Successful performance depends on the perception of possibilities for action, in other words, affordances. Affordance-based control dictates that actions are guided by moving so that it's always possible to perform the task within the limits of one's action capabilities. This means that actors must be able to perceive whether or not it's possible to perform the task within their limitations. An outfielder, for example, must perceive whether or not it's possible to catch the ball within the limits of their maximum running speed. The properties that are specified by optical variables in most information-based control models of visual guided action are not affordances. Rather, these optical variables specify that one's current state is or is not sufficient. These are different kinds of properties and are specified by different sources of information. To catch a fly ball according to affordance-based control, fielders adjust running speed so that it's always still possible to catch the ball within the limits of their action capabilities. So affordance-based control depends on the fielder's ability to reliably perceive whether or not a fly ball is still catchable. That is, they must rely on information about required running speed scaled to maximum running speed. Principle number 2. Possibilities for action are perceived directly from perceptual information in optic flow. Task-specific information in optic flow, properly scaled to actors' capabilities, directly specifies whether or not an action is possible. Thus, perceiving possibilities for action need not be mediated by a model of visual space. An outfielder should be able to directly perceive whether or not a ball is catchable without first estimating landing location and landing time. By comparison, model-based control asserts that visual cues to the ball's location and motion are used together with an internal model of the environmental dynamics to estimate the ball's landing location and landing time. These estimates are then used together with an internal model of the actor's body dynamics to determine catchableness. Thus, whereas catchableness is perceived directly from optic flow according to affordance-based control, perceived catchableness is mediated by estimates of landing location and landing time from a model-based perspective. Principle number 3. The perception of possibilities for action must be recalibrated following a change in action capabilities. This is something I didn't discuss much yet, but an obvious advantage of thinking about action capabilities in terms of intrinsic units is that it allows for their dynamic, ever-changing nature. Changes in action capabilities, for example due to fatigue, can easily be accounted for in terms of recalibration. See episode 120 for more details. Principle number 4. Recalibration involves the scaling of task-specific information in intrinsic units defined by one's action capabilities. Continuing with the idea of recalibration, model-based control accounts for this in terms of updating a general-purpose, memory-based internal model of body dynamics. By comparison, affordance-based control suggests that recalibration involves changing to the metric in which task-specific information is detected. This means that action capabilities, for example maximum running speed, are not explicitly represented anywhere. Rather, they correspond to the size of the units to which the visual system is calibrated. That is, there is no need for maximum running speed to be internally represented as a separate entity that exists independently of the perception of required running speed, as it does in model-based control. These two accounts of recalibration lead to very different predictions regarding the transfer of recalibration from one task to another. If recalibration results in an updating of a general-purpose internal model, then recalibration should easily transfer from one task to another, even if the two tasks involve different information. On the other hand, if recalibration is achieved by adjusting the metric in which information specific to the task of catching fly balls is detected, then recalibration should not easily transfer to other tasks that involve different information sources. So that is affordance-based control, a really intriguing idea that elevates the role of affordance perception beyond just action selection. For a more specific example of how it can be applied, check out Brett's study on interception, which I've linked in the show notes. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter @ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including an extra monthly episode and written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.